In this lecture, we are going to discuss another very important topic, multiclass classification. Previously, we discussed binary classification, which used a sigmoid at the output. We also had sigmoids for the hidden layer activation functions, but we just got rid of that in favor of the ReLU, which tends to work better. For the output, however, if we are doing binary classification, the sigmoid is still the right choice. Binary classification has many applications. We can predict disease or no disease. Is the user fraudulent or not? Will the user click my ad or not? Will the user accept a friend request or not? And so on and so forth. But there are situations that binary classification cannot handle, such as when we might have multiple categorical outcomes. Let's think of some examples. One example is optical character recognition or handwriting recognition. If we want to recognize alphanumeric characters, then there are at least 36 possibilities, 10 digits and 26 letters. What about speech recognition? If we want to recognize words, then each word counts as a separate category. Image classification is another one, and for a long time, this was the standard benchmark, which proved that deep learning worked better than other machine learning models. You may have heard of a famous dataset called the ImageNet dataset, which is made up of millions of images and 1,000 categories, such as bagel, vending machine, and soccer ball. Every year, there is a contest to see who can build the best ImageNet classifier, and of course, these are all deep learning models. So how does multi-class classification work? Well, suppose we have just calculated the activation at the final layer of our neural network, but have not yet applied the activation function. So we have A superscript L equal to W superscript L transpose dot Z superscript L minus 1, so that's the Z at the previous layer, plus B superscript L. It's important to remember that if the layer size is K, then A superscript L is a vector of size K. What we would like to do is map these values to probabilities for each of the K possible output categories. Okay, so that's your first lesson here. If we have K possible outcomes, then we should have K output nodes. The question now is, what function can actually map the vector A superscript L to probability values? Let's think about what the requirements are for these probabilities. We need a probability distribution over K distinct values. As a side note, we assign these values the integers 0 to K minus 1. First, since they are probabilities, they must be non-negative. In other words, they must be greater than or equal to 0. But there is also an upper limit. The maximum value of a probability is 1, but more importantly, for this to be a proper probability distribution, all the possible different values must sum to 1. So the second requirement is that all the probabilities must sum to 1. Luckily, there is a function that accomplishes exactly this. It is called the softmax function. First, let's drop the superscript L on the activation A for now, so we can just say A is a vector of size K. Then, the softmax of this vector A is the exponential of A divided by the sum of the exponential of A across each component. As you can see, this satisfies both of our requirements. The exponential of any number is always positive, so therefore, each probability must be non-negative. Second, because the denominator is just the sum of all the possible values of the numerator, then if we sum all the possible values of the numerator, we just get the same sum. And therefore, we get the same sum on the top and the bottom, and they cancel out to give us 1. Now that we know how the softmax works, let's answer the most important question. How do we use it in PyTorch? Well, just like most other functions we've applied so far, it's very simple. There is an object we instantiate called softmax. In other words, the only requirement is that you spell it correctly. Of course, you can always implement the softmax yourself, but in PyTorch, there's no need. As a side note, the softmax is considered an activation function, but unlike the ReLU, sigmoid, and tanh, It is not meant for hidden layer activations. If you want to try using the softmax as a hidden layer activation, you are most welcome to, but you'll generally find that it doesn't work that well. So the softmax is technically an activation function, but we normally only use it when we're trying to get an output probability from a vector of activation values, such as at the end of a neural network. Now that you know how to use the softmax in PyTorch, the next thing I'm going to tell you is to not use it. Just like we learned earlier with the sigmoid and the binary cross entropy, PyTorch combines those two functions into a single loss for numerical stability. So PyTorch is going to combine the softmax function with the cross entropy loss into this single loss, which is simply called cross entropy loss. PyTorch does in fact have a standalone categorical loss, which is called NLL loss, but that is outside the scope of this course. In the example below, we've implemented logistic regression, but instead of being a binary logistic regression, it's now a multi-class logistic regression that predicts k different categories. As you can see, the model is still just a basic linear layer. All the magic really happens inside the cross-entropy loss object. The last thing I want to do in this lecture is summarize the three types of tasks we've encountered so far that neural networks can perform and their corresponding activation functions. Two of them you already saw in the previous section of this course, and now we have a third. So first we have regression, where we use no activation function at all. Sometimes we also call this the identity function, which is just a fancy way of saying a function that returns its input. Second, we have binary classification, where we use the sigmoid activation function. Using the sigmoid, we only need one output node, because since we know the probability of the output being 1, the probability of the output being 0 is just 1 minus that. This is the same type of thing you see when you're looking at the Bernoulli distribution versus the categorical distribution. The Bernoulli distribution is a categorical distribution where there can only be two outcomes. Thus, it only has one parameter. The categorical distribution, on the other hand, if it has k outcomes, it also has k parameters. And that brings us to our third scenario, which is multiclass classification. For this, we use the softmax activation function. One important thing to mention that sometimes confuses people is that these three activation functions apply whether you are using a feed-forward neural network, a linear model, or even a more complicated network like a CNN or an RNN. It doesn't matter what kind of model you have. These three activation functions always correspond to these three tasks. So for example, if I don't want to use a neural network, but just a simple linear classifier for multiple classes, then I would have just a single dense layer with a softmax activation. This is still called logistic regression, by the way. It's just not binary logistic regression. Instead, it's called multiclass logistic regression. It's important to remember that what came before the final layer in the model is not related to the task. You can have a CNN or an RNN, or any other kind of complicated neural network. It is still the case that the final layer of the network will be a dense layer with one of these three activation functions corresponding to the task being done. Another important thing to remember is that the softmax function is more general. Whereas the sigmoid can only handle binary classification, the softmax function can handle multiclass classification, which includes binary classification. So it's possible, if you want, to just use the softmax for all types of classification. If you set k equals 2, then you're doing binary classification. It's just that in this scenario, your outputs are a bit redundant because you already know that they both sum to 1, and hence only one of them is really needed.